our discussion on influence line diagram construction for truss members. Okay, so tell me one thing that you know that in any truss member, which kind of forces you may expect? Anyone can tell?
Sir, axial forces.
Yes, only axial forces. Okay, either it will be tension or it will be compression. Will there be any bending or shear force coming in the truss member? Rama?
No, sir.
Yes, there will not be any bending moment or shear force coming in the truss member. Okay, so only axial forces will come in the truss member. So when we will be discussing about the influence line diagram for a particular truss member, then that you understand now in case of truss in such way, the influence line diagram for a truss member will be always for only axial forces, right? It cannot be like the beam where we have constructed where we have constructed the influence line diagram for a particular point for bending moment, shear force, etc. So in case of a truss member, first thing you understand that the influence line diagram for a particular member will be always consisting of axial forces. Okay, so let us try to understand. It's very simple to do. See, you have already learned about how to analyze a truss in your previous semester. Okay, in solid mechanics course you have learned about it. You have learned about the method of sections. Okay, so we'll try to use the method of sections only to prepare the influence line diagram for truss member, and step by step I'll try to explain you how you can prepare it. Okay, so let us see one problem, then you will be more clear on it. Okay, so let's say we have a truss something like this. So everyone can see the screen. Everyone can see the screen.
Yes, sir.
Okay,
Yes, sir.
so you see that draw the influence line for the force in member GB. So you see this is a truss. This is a truss. So there are many members AH, HB, AB, and this is the GB member. This is the GB member, one inclined member GB. So you are asked to find out the influence line for the force. What is the force? Force means the axial force in this member GB. So the influence line for the axial force in this member GB of this bridge truss you'll have to find out. So you'll have to construct the influence line diagram for this. Now if you want to construct the influence line diagram for a truss member, then you please remember that conceptual understanding process, that what we have done it for beam, that is not going to change. See, in case of beam influence line diagram, what we have done, in case of beam's influence line diagram also, we were running a unit load, single unit load, okay, without any dimension, right, over the beam. So in case of a truss, you must understand that the truss, when it is loaded, it will be loaded only at the joints. Okay, so a truss can be loaded only at the joints. That means the action point of the loads will be passing through the joints only. Okay, so when the action point of the loads will be passing through the joints, in that way, you see, in case of a truss member like the beam member, unlike the beam member, you have done it with a function of x, you may not be able to get the influence line diagram in that way, because it is not a continuous kind of process that you will have to put that load at every point in the member. You need not to place the load at every point in the member. That means, what I am trying to say, let's say you have one unit load, let's say you have one unit load something like this, and then you need not to pass this unit load over this beam, okay, sorry, over this truss member. Let me little bit thicker, let me make it. So let's say you have unit load, forget about this load. Let's say you have a unit load. This unit load, if it is entering from this side, you need not to consider, see, only at the joints you will have to see. So it's not that you will have to place this load at here and you'll have to find out what is the force coming in GB. You need to place this load at here and then you'll have to find out the load at GB. No, only you'll have to place these loads at the joints. That means where you'll have to place. This is one joint, so you place it here. This is one joint, 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 you place it here. So throughout this truss, okay, so this is the bottom chord of the truss, which will be actually, through which the load will be actually passing. And the load, when it will be passing through this truss member, loads will be only placed at the joints. That is very important, okay. So it need not to be a continuous kind of thing like you have done it for the beam, okay. So in case of beam, what you have done, we have placed it somewhere, then you have taken a distance from here to here, x, then we have found out a function in terms of x, and then we have put the values for x and found out what will be the shape of the influence line diagram, right. In the case of truss, you need not to do it in that way. In other way, you can say that in case of a truss, if you want to find out the influence line diagram for a particular member for its axial forces, then you only have to place the unit loads at the joints, okay. Is it clear? So if you place it at the joint, so every time you place the load at a particular joint, you need to find out what will be the force coming in that particular member for which you want to construct the influence line diagram. That means for this problem, you are asked to find out the influence line diagram for this member GB, right, for this member GB. So to find out the influence line diagram for this member GB, ideally what you should be doing, you should be placing the load at different joints. So you should be placing the load at here, and when you will be placing the load at this position, you need to find out what will be the axial force coming in GB. Then you come forward, you place the load at B, and then you find out what will be the force in member GB. The next joint is C, you bring the load at C, and then you find out what will be the axial force in GB. Then you move the load to D, you find out what will be the axial force in GB. You move the load to E, then you find out what will be the axial load in GB. Is it okay? Now see, every time what you are doing, every time you are finding out the axial force in the member GB for different position of the unit load at different points or different joints of the truss, okay. Now to find out the axial force, the easy method is to do with the method of section, okay. Now what is method of section? You have studied it in your solid mechanics course in the earlier semester, that method of section is nothing but you cut the member for which you need to find out the axial force. That means you need to pass a section through, that means something like this. So if you want to find out the forces in the member GB, so for method of sections, what you can do, you can just cut this GB member through a sectional line, something like this, right. So if you cut it something like this, then you see what you will get. You will get two different parts of the truss, and you can with after this sectional division of the truss member, total truss body, you can get the free body diagram for two parts of the truss, and from the free body diagram you should be able to find out what will be the force in the member GB. So step by step we will try to understand now how to find out the influence line diagram thus for this member GB. Okay. So the solution I have already shared with you in that PDF I have given earlier. So the solution is given over there. So you see, this is the problem actually we'll try to solve today. This is the problem actually we'll be trying to solve today. This is the influence line for the truss, and exactly the same problem you see it is handwritten over here. So you see, this is the problem we'll be solving. So basically this is the problem we'll be taking today. So this is A, B, H, G, B, G, C, D, E, G, C, then F, D, E. This is a truss, and for this truss, for this member GB, we are trying to find out what will be the influence line diagram. Okay. Now you see, first step what you'll have to do, I'll just try to explain in using this one. You see, this is the truss. Okay, this is the truss. Everyone can see this. What document you can see this in your screen? Is it visible?
Yes.
Okay. So you see, this is the truss we are taking. Now this is the member GB. So what I have said, what you will have to do, you will have to put a section over here, right? So if you put a section over here, that means if you are putting a section over here, that means what you are doing, you are just cutting this total truss using a line like this, and you will be dividing the truss in two parts, right? So how this, after this section finding, how it will look like? You see, the thing will look like something like this, isn't it? The thing will look like something like this. So what you have done, you have passed a section, this one. So what you have done, you have passed a section something like this. See what you have done, you have passed a section something like this, and because of this section, you see, the truss will be getting basically divided in two parts, right? So these two parts, when you will be taking these two parts, when you will be taking, you see, you will have one portion on this side and the other portion on this side. Okay. So once you have this section, either you can consider the equilibrium of this side of the section, or you can consider the equilibrium of this side of the section. Okay. So anyway, whatever part you want to find, you can find out any part of this section, and you can find out the force in this member GB. So you see, this is the member GB. So this GB member is now cut. So whatever force will be coming on this portion of this, that same force will be coming in this portion of the truss. So there will be either tension or there may be compression. There will not be any kind of bending and shear force coming. Okay. Now let us try to understand how will you find out. So let us see. If we try to just do it using this portion of the section, let us say the first step. What will be the first step to find out? So for finding out any member force, what is the first step you do? First step will be to find out the reaction at this A and reaction at this E, right? So what will be the forces, what will be the reactional forces in A and E? See, in case of A, you will be getting a vertical force something like this. So there will be vertical force at member A, and there will be vertical force at member joint E. So there will be two reactions. So this is your RA and this is your RE, isn't it? So there will be two reactional forces. So let me change the color, then it will be more visible. So on color, let us make it gray. you see, you get two reactions, right? Now if you want to find out reaction, you must understand one thing. See, when you will be finding out reaction, you see, for every position of this unit load 1, you will have to find out the reaction, okay, for every position of this unit load 1, because when you see, when the load is here, your reaction will be different. When the load will be moving to here, your reaction will be different. When the load will be coming here, your reaction will be different, okay. So let's say at the first position of the load, that means when the load is at, let's say at B, then what is the reaction at A and what is the reaction at E? So how do you find it out? If you go to this, so you see, I have explained over here. So you see, this is exactly the same truss we are showing. So this truss member, this is your reaction at RA, this is the reaction at RE, and the load is acting over here. So what you will have to do, if the unit load is acting at B, at that position, when the unit load is acting at B, at that position, you see, you will have to take moment about this point E. So if you take moment about point E, that should be equal to 0. So if you take moment about this point E, what will be the moment? See, this is your RA. So you see, what will be the moment? Just try to bolo.
RA into 24
RA
minus
into
1
24
into 18.
very good, 1 into 18, very good. So this will be your, this
zero.
should be equal to 0, right? So from this you should be able to find out RA. So RA is going to be equal to 18 upon 24, right? So there will be some value you will be getting, and that calculation is shown over here. So RA 18 by 24, that is going to give you value of 0.75. So you see, you are going to get a value of 0.75. Okay. So what you have done, you have found out the value of RA. And RA for what? RA, because when the load is acting at the joint B, and what is the load? The load is the unit load of dimensionless quantity. Okay. So once you found out RA, so what will be your RB? So you see, from the equilibrium condition, RB plus, sorry, RA plus your RB, little bit larger I should make it, otherwise. See, RA plus RB should be equal to how much? Bolo?
1, sir.
It should be equal to 1. Why it is 1? Because this is the downward
Sir.
load. Yes.
RA plus RE, sir.
RE, yes, sorry. Very good. RA plus RE should be RE should be equal to 1. So what will be your RE in that case? So what will be your RE?
0.251 minus.
Yes, 1 minus 0.75. That is going to be, sorry, 1 minus, it will be minus 1 minus 0.75. That is going to be equal to, so next line will be right. So it will be equal to 0.25. Is it clear? So what you have done? You have found out the reaction, right? So RA you found out and RE you have found out. So RA, once you know the reaction, then what you can do? After you found out the reaction, you can take this method of section and you consider this part of the truss. Okay. Now let's say you don't worry about in which direction the forces are acting. Okay. So this is what you should do actually. So let's say on these three members, one force is acting in this direction, other force is, let's say, acting in this direction. All arrows, you see, we are taking outward direction. Okay. You don't worry about it. If in this outward direction, if you are getting the value in the outward direction as the same or the positive value after calculation, then your direction assumption is correct. Okay. Otherwise your just direction of the force will be just getting reversed. Okay. So that is how we generally do, right? So format save, let me just just make it little bit bolder. Then so see, for these three members, so we have taken the right side of the truss, after making the section, and we are just putting the member forces in the truss. Okay, so once we have put the member forces in the truss, what you'll have to do? See, you know now what will be this force, what is this member, you see, you go at the above and you see what is this member. This is your GH, right? This is your GB and this is your BC or CB. So you see three forces. So this is your FG, what? This is your FG, bolo? FGH. This is your FGH. So this horizontal thing is your FGH. This one is your FGH. This is your FGB and this is your FBC, isn't it? Should I bring this truss again down? Then it will be, maybe let me bring it little bit down, then only will be clear. So again I put it over here, then only will be able to understand. See, now is it clear? So this is where we have taken the section. So see, what will be this force? This is your GH member. So this is going to be your FGH. This is going to be your FGB. This is going to be your FBC or CB. Okay. So you again go back to this. So you see, we have now, when the unit load is at B, we have found out what is the reaction at RA and RE. That we have understood. Now we are using method of section. So in this method of section, you see there are three forces. Along this it is FGH, this is your FGB and this is your FBC. That's what exactly I was telling. FGH, FGB and FCB or FBC. Okay. So you see these forces, when it is acting, you see this member is 6 meter and this height of the truss is also 6 meter. So what will be the angle? See, this is actually a right angle triangle. So this is 6 meter, this is 6 meter. Okay, so base is 6 meter and the height is 6 meter. So when the base and height both are same, you see tan theta is going to be how much? Tan 45. Yes, exactly. Theta is going to be equal to 45. Tan 45 degree is equal to 1, right? So it is this angle of the truss. So this angle is going to be 45 degree. This angle is going to be 45 degree. This angle is going to be 90 degree. Exactly the same way, if you come to here, see this angle is going to be 45 degree. This will be 45 degree. This will be 90 degree. So this angle exactly. So if I can show it here, see with this. So basically this angle is going to be your just I am showing it with a straight line. So this angle is going to be actually 45 degree. So if you take the equilibrium of this portion, then from the free body, how do you calculate it? See, you know the load is at this position B and you are taking the equilibrium for the right portion of the truss. So if you take the equilibrium of this position, you see what you have done, you have calculated what is the value of RE. So you see, you have calculated the value of RE. So what is this value of RE? This value of RE for this position of load, that means when the unit load is at B, the value of RE is equal to 0.25. Now you consider the equilibrium of this portion of the truss and try to find out what will be the value of FGB. Okay, So if you want to find out, what you'll have to do, what you can do, you can just consider the vertical equilibrium of this member. So this is your FGB. So what you can write, you see, very simply you can write something like this. So if this angle is 45 degree, this angle will be also 45 degree. So the component of this force, that means if you resolve this force, so this force is nothing but your FGB. You see, this force is nothing but your FGB, and this is your FGH. So if you vertically resolve it, you see, you are going to get one horizontal component of this force and one vertical component of this force. And if you take the vertical equilibrium, that means if you just do the summation of all the forces in the y direction as 0, that means sum of all the forces in the y direction as 0, that means summation of Fy is equal to 0. If you do, you see what you are going to get. So this is your FGB. So you see, you are going to get something like this, that FGB, so FGB, this will have a component, of, if this is 45 degree, see, if I resolve this force along this direction and along this direction, then FGB cos 45 degree will be along this horizontal direction, and this FGB sin 45 degree will be along this direction. That means if I resolve this force along this and along this, that means if I resolve it along this direction and along this direction, so what I am going to get, if I take this vertical resolution of this force, then you will get FGB sin 45 degree. So you are going to get FGB into sine of 45. Okay, degree I am not writing. So if you see FGB sine 45 degree, this is acting in the downward direction, and if you consider the y direction upward as positive, then what you should do, if downward direction we take as negative, then we will write FGB in front of it, we will put a minus sign. So minus of FGB sin 45, this is acting downward. You see, this is acting downward. And what is the upward force, vertical force acting in this? This force is acting. And what is the value of this? What is this? This is actually nothing but your reaction at E, and we have calculated the reaction at E. What is the reaction at E? Reaction at E is, yes, 0.25. So that should be equal to 0, isn't it? So you see, now let me go back to that handwritten solution. So see, this is what we have done. So summation of Fy equal to 0. So minus FGB sin 45 degree plus 25 is equal to 0. Have you understood? So see, here I have explained it in more detailed manner. Okay. So you see, FGB, there will be a cos component, there will be a sin component. So why we are taking minus sign? Because the downward directional loads will be taking as negative. Okay. So F minus FGB sin 45 plus 2.25 is equal to 0. So if you find out this solution, then FGB is going to be equal to, so you can find out your FGB value thus. So FGB you can find out, finally you will be getting FGB as the value equal to, it will be 0.25 divided by sine of 45 degree, and if you do sine of 45 degree FGB, then your value will come to approximately, it will come to 0.353. So it is going to be 0.353. Okay. Now see, I have written here, in this case, you see, by the side I have written here, it is tension. Why I have written it is tension? Because you see, in the member I have assumed this load is acting as a tensile force, okay, and I got a positive sign. That means the assumed load direction is correct, okay. So this FGB thus will be positive or it will be tension, okay. Suppose instead of this direction, if you would have taken this load in the reverse direction, then you see you would have getting this value of FGB as negative, okay. So if it is coming negative, then you see you will have to reverse the direction of the force and you should be writing it again as tension, okay. So next point sorry. So see, first what you have done, for the position of the load at B, for the position of the load at B, you have calculated what is the value of force in this member GB. So exactly the same process now you will have to follow for other points. Other points means, what are the other points? Someone tell me. Bolo. C, point C, point D and point E. Point E, not F. Why F? The load is moving along the girder, right? This big bridge deck girder. So we will be considering only these joints, this joint, this joint, this joint, this joint, okay. So next position of my load, see the first position of load was here, okay. So if I now move this load from here to here, okay, then what will happen? So tell me. So if the load is now moved from, let's say the load is now located, let's say at here, okay. So if I move this load at this position, then you tell me what will be. So the load, let's say this one load from here, it has come to this position. Now for this position C, again you will have to find out what is the reaction at A and what is the reaction at E, because you see at the position B, when the unit load was there, reaction was different. When it will move over to C, the reaction at A and reaction at E will be different. Now tell me, someone please tell me, what will be the reaction at A and E in that case? Can anyone tell?
So we will take the moment
About E only, okay. So we will take moment about
RA
E
into
only.
24 minus 1 into 12.
Yes, very good. So RA into 24, only the change will happen over here, right? So 1 into 12 will come into picture, right? So this will become RA is equal to 12 by 24. So this reaction will become 0.5, isn't it? 12 by 24 is half, so it will become 0.5. And RA plus RE, obviously it is going to be 1, correct? Because you see, don't think this load is not there, okay. So I cannot remove it because it is pasted in Word document. So see, this load is not there. You see, this load is not there. Please understand, this load is not there. This load is actually this load has actually moved to C, okay. Now it is the location of the load is at C, right? So when the location of the load is at C, again you see this RA plus RE will be equal to 1. So RA is RE will be how much? Your RE should be equal to R1 minus RE, RA, and RA is nothing but we have calculated 0.5. So you will get this as 0.5. So your RE is 0.5, your RA is 0.5. Now again what you will have to do? Again you will have to take method of section, and again you will have to find out what is the value of GB, okay. Now again let us come down, and we have taken the method of section. We are considering the equilibrium for this portion of the body. Now you understand one thing, at this position when we are considering the equilibrium, you see very carefully, you observe it. Now you see the load is not on this side, not on the left side of the section. The load has already come to the right side of the section, isn't it? Because load is now at C. So you will have to consider this load also while considering the equilibrium. If you do not consider it, then the thing will be wrong. Okay, so you see this is the unit load. So this is the unit load is now at the point C, and because this load has now come to the right side of the section, that is why you will have to consider this load also while considering the equilibrium. Okay, so what you have to do now? If you want to consider the equilibrium for this, then exactly the same way you have done it. We have done it, sum of all the forces in y direction as 0 you will have to do. So sum of all the forces in y direction, when it will be you will be doing it as 0, then what will be the equation changing? How the equation will be changing? Can anyone tell me?
Sir,
Hmm.
it will be, sir, plus 0.5, sir.
So it is going to be minus FGB sine 45, because this, yes, FGB sine 45, then after that there will be another one minus 1, right? And what will be this? What will be this? Is it going to remain 0.25? This RE,
No.
what will be the value?
0.5.
Yes, very good. So this is 0.5, you have got it. Okay, so this will be the equation now, the changed equation for the equilibrium when the load is moving to C. The changed equation will be this one. This is very simple, you see, this is method of section. Okay, just step by step you will have to do it. Okay, so if you solve it, then what you will get? So minus FGB sine 45 minus 1 plus 0.5. So this minus 1.5, that means it is going to be 0.5 plus, right? So it is going to be 0.5. If it goes to the other side, it is going to be 0.5, and you are going to get a minus sign because minus FGB is over here, right? So you are going to get a minus sign. So you are going to get the value something like minus 0.5 by sine 45 degree. Let us go back to the handwritten solution again. See, that's what we have done it here. See, when the unit load is at C, you see this is what we have calculated, RA and RE, and you see the equilibrium, the vertical equilibrium, if we consider, then summation of all the forces in the y direction is 0. So this is the equation we have written, and you see finally we have written FGB is equal to minus 0.5 by sine 45, and this is what we are also getting, minus 0.5 by sine 45. Okay, and if you calculate this value, you are going to get a value of minus 707. Okay, so minus 707. So the value will be equal to minus 0.707. Now you see what is the difference with the previous one. See, we have assumed this load, this force in the member GB in this direction, right? So in the previous case, when the load is at B, at that time you see we have got a positive sign, right? When the load is at B, we have got a positive sign for FGB. So that means our assumption, whatever we have taken, that was correct, and we have considered that force as, so that means the force was tensile force. Now in the second case, you see you are getting the value as negative. So once this value is negative, that means this is not remaining tensile. You have assumed it as tensile, but you are getting a negative value. That means it is not tensile, it is compressive. So it will be, it is compressive. So this is C. Okay, so have you understood it? So this first one is your tensile force, and the second one, second position of the load. So when the load is at B, it was tensile. When the load comes to C, it has become compressive. Okay. Now what will be the third case? What will you have to do for the third case? Bolo?
We'll shift that load in D, sir. from
Yes,
point D.
very good. Yes. So you shift the load to D. Correct. You'll shift it over here. So if you shift it to D, now you see, you know, oh, sorry. What you'll have to do? You'll have to find out what is the value of reaction at A and reaction at E. So when the load has been shifted to this point D, then what will be the reaction at A? Again you consider moment about E. So RA into 24 will remain same. Now what is the distance of this load, this unit load to E? The distance is 6 meter. So yes, instead of 1 we will be multiplying it with 6, and your RA is going to be equal to 6 divided by 24. Okay. So what will be the value here? It will be 0.25. Correct? 0.25. 6 by 24 means 1 by 4. 6 4 ja 24, so it is 1 by 4. 1 by 4 means 0.25. So once you have calculated your RA, again your RA plus RE will be equal to 1. And what is your RA? RA is nothing but your 0.25. So 1 minus 0.25. So this is going to be RE will be equal to 0.75. Okay. So have you got it? So you see, for the third position of the load, that means again we will be considering method of section, and the load will be moving over here from here to here. So it is coming to D. Okay. So when it is coming to D, at that time what is the value of RE we have got? We have got the value of RE as 0.75, isn't it? So we have got the value of RE as 0.75. So again you take the equilibrium, vertical equilibrium of these forces. Again you take the vertical equilibrium of these forces. So how do you calculate the vertical equilibrium? So again it will be below minus FGB sine 45. Then here it will be, this load is has now come to D, so it will remain minus 1. And then what will be this load? What will be this load? What will be this reaction? 0.75. Correct. So how much will be the value? Minus 0.25 by sine 45. Minus 0.25 by sine 45, right? So if you go back again to this handwritten solution, let us see what is being done over here. See this unit load at C. Unit load at C. So RA into 24, 1 minus 12. That's what we have done it. Then we are taking the equilibrium, vertical equilibrium. So this is what we have done. Is it no, sorry, not this one. Third one, this one. So see, RA into 24 into 1 minus 6. So RA is going to be 0.25. RE is going to be 0.75. That's what we have done. And then we are getting this value, this one, minus FGB sine 45 plus 0.75 minus 0.1 is equal to 0. So you are getting minus 0.25 by sine 45. So how much value you are getting? So again you will be getting a minus term, 0.353. So again you are getting a value with minus sign, so 0.353. So will it be tension or compression? Will it be tension or compression?
Compression, sir.
Yes, it will be, yes, compression. Okay, so it will be compression. Okay, so see that is what we will have to do. So you see what you have done, for every position of the unit load at not every position, for the position of the unit load at the joints, different joints of the truss, what we have done, we have calculated the member force in this member GB, right, in this member GB, and we have got the values of the member forces. Now if we plot them, then we will be getting the value of the, you will be getting the influence line diagram for the truss member GB. Okay, now you see again, let us go back to this slide and sorry, this one, and see. So see, three values we have got, right? Three values we have got. So see, when the load will be at this, when the load will be, when the unit load, when the unit load will be, sorry, when the unit load will be at this A, or the unit load will be at this E, at that time you see the values of the reaction, values of the member force at this GB is going to be equal to 0. That you understand, right? So if that is the case, then if you plot it, so when the load is at A, it is 0, you see, and then if you are moving, and when you are going to a 6 meter length, when you are going to the 6 meter length, that means 6 meter length means when the load is placed over here, when the load is placed over at the point B, at that time what we have got, we have got a tensile force. You see, when the load is at B, we have got a tensile value of 0.353. so you plot it, tensile, sorry, you plot this tensile 0.353, tension means on the top side you will do, and then join it with a straight line. Okay, then you see, when you will be going to this 12 meter length, when you will be going to this 12 meter length, that means when you are coming, and when you are placing your load over here, that means 6 plus 6, 12 meter length, then also we have found out in this that the value is minus 707, that is compressive. So minus, we will be plotting it down. So at 12 meter, the ordinate of influence line diagram, so this value will be minus 707, and then what you do, you just add it with a straight line. Okay, now you see what will be the value at this 18, what will be the value of this value of the member force at this 18 meter length. That value of the when the load has been moved from C to D, you see the value of the member force we have calculated, this is minus 3.53, minus 0.353. so again you plot it over here. So minus means this ordinate at 18 meter distance will be 0.353. so you see, we have got this ordinate as 0.353, and then again you join, because at the 24 meter length it will again become 0, because the load will be now just reaching the support, and thus this at this point it will again become 0. So you join it with a straight line. Okay, and thus you will be getting the influence line diagram for the member GB. Is it clear? So this is what is the process for influence line diagram for the truss member, and you see the solution, final solution I have shown here. So this is nothing but this one. So X FGB 0, 6, 12, 18, 24, every point you do it, and then you plot it like this, and this is actually your influence line diagram for FGB. Exactly the same problem is solved in a handwritten way in the handout. Okay, so you please go through and work your own. Okay, otherwise it will be difficult. Okay, otherwise it will be difficult to work out the problems. Okay, so is it clear to everyone? If you have any doubt, you can ask now. Okay, so is it clear? See, step by step I tried to explain you. Okay, but still if you have any doubt, you can ask me. Okay, and
Sir, if two loads were given,
two loads, see,
Yes,
that is what I am saying. See, now see, this is what is the influence line for this member GB we have plotted. Influence line for this member GB we have plotted. Okay, after this let's say a 10 kilonewton load is moving over this truss. Okay, let's say 10 kilonewton load is moving over this truss. Then what will be the maximum axial force? What will be the value of the maximum axial force at GB? How do you find out? So first you will have to draw first you will have to plot the influence line diagram. Okay, so see where are the ordinates maximum? You see the positive force, that maximum tensile force will occur over here, right? So what you have to do, this 353 ordinate value is the maximum positive ordinate value. So the maximum tensile force which may occur at the member GB because of 10 kilonewton load will be 10 multiplied by 0.353. And what will be the maximum negative value of maximum compressive force which may occur in the truss member? That will be equal to 7.707 multiplied by 10, because this ordinate is your maximum ordinate. Okay, now you see, if the multiple loads are moving, if a series of concentrated loads are moving on the truss, okay, then what will happen? Okay, so exactly the same process we have discussed or we have understood in case of the beam member, that you will have to follow. Or otherwise what you will have to do, you see, when the series of concentrated load will move over a truss member, you see only the loads, point loads, instead of the particular point in case of a beam bending moment or shear force influence line diagram, instead of that, in case of a truss member, what you will have to do, the loads must be going through the joints. So if the series of concentrated load is there, then you will have to place the point loads on the joints, okay, and then you will have to find out if a UDL is there. So because of a UDL, what will be the value of axial force? See, for if a complete UDL is over this truss, okay, so see this, for this portion, if the UDL is totally on this truss, then total area of this multiplied by this value of this UDL is going to give you what is the force in the member. So this is going to give you the negative or compressive force in the truss member. On the other hand, if you want to find out what is the maximum positive truss member, then what will maximum tensile force in the member, then what you will have to do, you will have to take this triangle, you will have to take this triangle and multiply area of this triangle and multiply it by the load or the UDL, whatever you have. So the process of finding out the total bending moment or total axial forces exactly will remain same as we have discussed it for the other cases of bending moment and shear force influence line diagram for beam members. Okay, is it clear, Abhishek?
Yes, sir.
Okay, now you see, there is another one problem, solved problem is given. Okay, I am not explaining it in the class okay, so I will advise you just see this solution. Okay, so this is the handwritten solution. Okay, you just follow this solution also. So this is another one kind of problem. Here the point someone, Abhishek or someone has raised, that how to find out the if other loads are moving on the member. So this problem will explain it. This 20 kilonewton and a uniform live load of 0.6 kilonewton meter is moving over the truss. Then you see, first step is always to find out the influence line, and then after you find out the influence line diagram, you just have to put the load at proper place where the maximum ordinates will come, or for UDL you will have to find out the area and then find out the value of the total axial forces. Either it may be compressive or it may be tensile. So I'll request you please go through this problem. Okay, this is another one problem, good problem, and for that problem you see this is the influence line diagram, and for that influence line diagram I have shown you how to find out because of this point load. See, the things are remaining same, exactly the same way. So maximum ordinate, so point load, when it will come over this ordinate, then it will give you the maximum value of tension or compression. So 1.33 multiplied by 20 we have done, and then if the UDL is totally over this truss, then total area of this truss is being total area of this influence line is being taken and then multiplied it with the load. So this 80 kilonewton load is moving over the beam, I think 80 kilonewton or not 20 kilonewton load. So 20 kilonewton load is moving over the beam. So no, sorry, this is 20 kilonewton is the point load, and how much is the uniform load? Uniform load is 0.6 kilonewton meter. So 0.6 kilonewton meter load is moving over the beam. So 0.6 multiplied by the area of the influence line. So this is your area of the influence line, and from this area of the influence line, if you can easily get the amount of tensile force or compressive force on the member. So you see, you must understand one thing, that different problems will give you different types of influence line diagram, and it is only from observation or from practice you will be able to understand where you should place the load, so that you will get the maximum value of tension or compression in a truss member. Otherwise the method of finding it out remains exactly the same. Okay, so let me finish the class of today. So I will take the attendance and then we will stop. 26, refresh. Okay. Okay, thank you.
Thank you.
Thank you. So next week we'll start with the discussion on arches and then cable, then portal frames. Okay. So step by step we'll take up those things. How to analyze arch, truss, and portal frames. Okay. Okay. Thank you. Thank you very much.
Thank you, sir.
Hmm.